Okay, guys, 16 part 2, here we go, combining complex numbers. I just want to recall what we did yesterday and how I showed that every complex number has got two representations, a Cartesian form and a polar form. And depending on what you want to do to the complex number, sometimes using the Cartesian form is better, sometimes using the polar form is better. In summary, just to kind of put this into your brains, if you want to add or subtract complex numbers, you should use or you must use the Cartesian form. If you want to multiply or divide complex numbers, it's much easier to use the polar form than the Cartesian form. And so you should use those, although you can actually do it in Cartesian form, as we've already seen. Okay, so let me just kind of recall what we did yesterday. I showed this. So I'm going to go from Cartesian to polar. And I'm going to look at the number, we say minus 5 minus I to polars. Okay, so I want to convert the Cartesian form, which is a number plus a number times I, into polar form. And so the way you do this, of course, is you first off you draw your little Argand diagram, and you have minus 5 and minus I, so it's 1, 2, 3, 4, 5, and then minus 1. So the point is down here, and this is you draw your line up here, and you want this angle alpha. Call this angle here alpha. Now you know the length here is 5, and you know the length here is 1. So therefore, tan of alpha is 1 over 5. So therefore, alpha is tan inverse of 0.2. Make sure you're in radian mode, folks. And I got 0.2 here for alpha, approximately to 1 decimal place. Now, how many decimal places you take is up to you, but I'm just taking, I took 1 decimal place. I think when I got tan inverse of 0.2, I got 0.199 or something. So I'm going to take it down to 1 decimal place, 0.2. So then for then theta, the argument of the complex number, don't forget to do this now, folks. The argument then is the angle made by the line connecting the point to the origin and the positive direction of the real axis. So therefore then theta, which is what you want, the argument then is pi plus 0.2. And when I did that, I got 3.34. Okay, so then the polar form then, so therefore, and we know what r is always the square root of the first one squared, which is 25, plus the second one squared, which is 1, so it's the square root of 26. And so therefore, minus 5 minus I, you can also write that as the square root of 26 exponential I 3.34. And if you want to get the square root of 26, which is about 5.1 something, you can do that as well. And if you want to do that, why not? So let's just take it as 5.1. I don't know what the exact one is, but let me just put it as 5.1, 3.34. Okay, so there you go. So this form here, the polar form, is exactly the same. It's just the same complex number written in a different way using De Moivre's theorem. So that's converting. So converting from Cartesians to polars is sometimes tricky because you have to mess around with the angle alpha and you have to mess around with theta. Calculating r is very straightforward, but it's actually difficult. But going the other way is actually very, very easy. Converting from polars to Cartesians is trivial. So I want to look at, so this is P stands for polar, C starts for Cartesian. So I want to look at the number 6 exponential 2i. So 6 exponential 2i, it's very, very easy because you just use the Moivre's theorem. It's cos of 2 plus I sine of 2. So do not forget that, guys. The whole, as I say, complex numbers analysis is based on going from a complex exponential to the sum of a cos and an I times sine. So all you do is you replace, you take the number multiplying the I, and you write it as cos of that number plus I sine of that number, whatever the number multiplying the I is. And then you multiply that in here, guys, you get 6 cos 2 plus I 6 sine 2. And I just bashed out in the calculator, I got minus 2.5 plus I 5.46. something like that. Yeah, so you just, maybe I made a mistake there when I messed up with the calculator. But as you see, going from Cartesians to polar is hard. From polars to Cartesians is very, very easy once you remember what the Euler's theorem. Okay, so now let's again come back and look at combining complex numbers. So I want to look at addition. So let's see. Suppose I want to add these two complex numbers. So I got minus. So remember, we've got two complex numbers here. Let me call the first one complex number 1. So Z1 is this one here. It's minus 5 minus I, and that's equal to 5.1 exponential I 3.34. So that's the first point we looked at. So they're exactly the same, different forms of the same thing. So the first complex number is either minus 5 minus I or 5.1 exponential I 3.34. The second complex number then is this one here. So it's minus 2.5 plus I 5.46, and that's equal to 6 exponential 2I. Now suppose I want to add Z1 plus Z2. Now, if I want to add these two complex numbers, now, as I say, guys, each complex number has two forms, Cartesian or polars. If I want to add these complex numbers, Z1 and Z2, I can't use the polar form. I always have to use the Cartesian form. So in this case, if I want to add two numbers, I forget about the polar form and just add the Cartesian form. So here I get minus 7.5 and then plus I 4.46. And similarly, if I want to get Z1 minus Z2, it's minus 5 minus I, and then minus 2.5 plus I 5.46, whatever that is. So if I want to add complex numbers or subtract complex numbers, I must use the Cartesian form. And if I'm given two polar forms, I must first convert to Cartesian form before I can add and subtract. That's a very important little idea. But where polar forms come into their own is when I'm multiplying or dividing complex numbers. And then you should probably, if you have a choice, use the polar form. So let's look at multiplication. I want to multiply Z1 by Z2. Now I have two ways to do it, folks. I can take the Cartesian form, so look, Z1 and Z2. So it's minus 5 minus I by minus 2.5 plus I 5.46. That shouldn't be there. So you get I 5.46, they're the two Cartesian forms, and you multiply in then, you get minus 5 by minus 2.5, minus 5 by 5.46 by I, and then minus by minus plus 2.5I, and then lastly then you get minus I squared 5.46. And I squared is minus 1, so you have to be careful with that. I think that is 7.5, but I might be wrong. It's not 7.5. It's 12.5, isn't that right? Minus 5 by that, so it's 12 plus 2.5. So I think it's 10 plus 2.5, so it's 12.5. And this is minus plus 5.46. And then you have an I term then, you've got 2.5 minus 5 multiplied by 5.46. I'm not going to multiply it out. So that's the multiplication. So as you can see, when you multiply the Cartesian forms of complex numbers, it's a little bit messy. On the other hand, or, here's the or, folks, oh, this is going to be exciting. If I use the polar forms, it's very, very easy. So it's 5.1 exponential I 3.34 times 6 exponential 2I. So if I want to multiply now Z1, Z2, and I use the two polar forms, I multiply the two moduli together, so that should be 5.1 here, folks, sorry. So 6 by 5.1 is 30.6. And when I multiply two exponentials, I add the arguments. So 2 plus 3 is 5.34. And if you got the Cartesian form of this now, you would get exactly the same as this. But as you can see, if you multiply the polar forms, it's trivial. You multiply the two moduli together, and you add the arguments. So that's how you do multiplication using the polar form. And as you can see, it is much simpler using the polar forms. So if you have a choice, you should use the polar form. Now you can actually use the Cartesian form, you can multiply it up, and that's fine. And perhaps if you just have the Cartesian form, you just do it this way. But if you have a choice, you should always use the polar form. And it's exactly the same with division. So division even more so perhaps. So if I look at Z1 over Z2, and Z1, guys, again, is, if you go look at the Cartesian form, it's minus 5 minus I over minus 2.5 plus I times 5.46. And then what you must multiply that by is the conjugate of what's below. So if you remember back to your secondary school days, if I want to divide the Cartesian form of two complex numbers, I must multiply above and below by the conjugate of the denominator, the number below the line. And so in this case, it's minus 2.5 minus I 5.46. And so you do the multiplication above, you do multiplication below, and you get your answer. Can I put etc. here? So that's a little bit tedious, and it's a lot long-winded. Or what you could do maybe is you could use the polar forms of the two complex numbers, Z1 over Z2. So Z1 over Z2 is 5.1 exponential I 3.34 over 6 exponential 2I. So remember now, guys, these are the polar forms. They're the same complex number written in a different way. So what you do here now is you want you to subtract, you divide the moduli. So you get 5.1 over 6, whatever that is. I don't have a calculator in front of me. You just bash that out on the calculator. And when you're looking at the complex numbers now, one complex number divided by another complex number, you subtract the arguments. So it's exponential I 3.34 minus 2. That's all you do. So you get that from this, whatever that is on the calculator, 5.1 over 6, exponential I 1.34. And that's your answer. So as you can see, dividing complex numbers is really trivial once you have the polar form. You divide the moduli and you subtract the arguments. So that's a very, very important one. Finally, in this exciting part of the lecture, I'm going to talk about exponentiation. And exponentiation is where you have a power. So you've got a complex number to a power. You have to use complex number, or you have to use the polar form here when the power is very big. Let me show you. Let me just show you. This is the last thing we're going to do. It's called exponentiation. I'm sure that's not how you spell it. Exponentiation. It doesn't matter. It's complex numbers raised to a power. So let me just take one of these complex numbers here. Yeah, I'm just going. Yeah, let's just take this one. So let's look at minus 5 minus I to be squared. Okay, so that's just that's equal to minus 5 minus I by minus 5 minus I, and you just multiply that out. Then you get 25 minus 10I. No, plus no, yeah, minus plus 10I, yeah, and then minus I squared. Now, hopefully, I've been careful, but maybe not. So it's 25 minus plus, so you get 10I here, and then minus by minus gives you plus I squared. And I squared is minus 1, so I think you get 24 plus 10I. Now, just make sure that I'm doing that correctly, folks. I think that's okay, but you do have to be careful with the minus signs. All right, so that's fine. You can do that, but what about something like minus 5 minus I to the power of 24? So when you've got very large powers, that means you must multiply minus 5 minus I by itself 24 times. And I would suggest to you guys that life is too short to do that. Really, you just have to, that's just, you're going to make a mistake. It takes too long. But this kind of calculation occurs sometimes in complex numbers. You have a complex number raised to a large power. In that case, what you should do is you should convert the Cartesian number into its polar form and then do the calculation. So if you remember, -5 minus I, we said it's the square root of 26 exponential I 3.34. So can I write that down? To the power of 24. So square root of 26, that's 26 to the power of a half. So you can now you're multiplying the modulus by the exponential, brackets a power. You can bring the power into each of the individual terms. So that's 26 to the power of a half to the power of 24. Exponential I 3.34 to the power of 24. So 24, a half multiplied, so that's 26 to the power of 12, folks, whatever that is. It's a big number. And this complex number then is when you have an exponential to a power, you just multiply the powers. So you get exponential I 3/34 multiplied by 24, whatever that is. So when you've got a power which is a large number and you've got the Cartesian form, you should convert the Cartesian form to the polar form and then do the calculation. So when you do it that way, using the polar form, you can get an answer very, very efficiently and rapidly. So in this case, what you get is 26 to the power of 12, whatever that is. Exponential I don't have a calculator with me, but you multiply 3.34 by 24, and that's your answer there. That's your argument inside there. So be very careful. If you have this, and this is an important little calculation of complex numbers, a complex number raised to a power, always convert to a polar form, and then bring the power into each of the two individual parts, as I did here. And the first part is very straightforward. And the second part then, if you want to get the power of an exponential, you just multiply the arguments. So it's very, very easy. Now, you could not do that using the Cartesian form, but it's very, very easy using the polar form. Okay, so that's combining complex numbers. If you have addition and subtraction, you should use the Cartesian form. If you've got multiplication or division, you should use the polar form. And if you have a complex number to a power, and especially to a large power, you must use the polar form. And we'll talk about this more tomorrow, which will be pretty much our last lecture. And then the one after that, then I want to go back over some exam questions for you in lecture, whatever it is. I don't know what this is, 16, so 17, 18. In lecture 18, I'm going to go back over and look at some past exam questions, which is just basically the stuff that we did today, actually, most of the time. Okay, guys, enjoy your, this is on Easter Monday. I think this is Monday. Who knows anymore? I think this is Easter Monday morning. Enjoy the rest of your Easter if you can, and I'll talk to you tomorrow. Okay, bye-bye.